All right, y'all, we are checking out 8B out of the text. It's arc length and sector area in our second part of our trig unit. Before we jump too far in, I wanted to give you a little vocab. Just make sure we're all speaking the same language. So a circle is all of the points that are the same distance away from a central point. That distance is called the radius. That runs from the outside of the circle to the center. If you run a line from the circumference to the circumference that passes through the center, that's called a diameter, and it's twice the radius. You know that. There's a couple other pieces. If you walk all the way around the edge, you walk the circumference, like circumnavigate. If you take just a piece of that circumference, it's like the crust of a pizza. That's called an arc. You've taken an arc, or maybe an arc length. And the area of that pizza slice, if you cut out a slice of pizza, is called the sector. So the sector area. The other interesting part, there are pieces called segments. And a segment is, if you draw a chord goes from one point to another, not through the center. The area bounded by that chord and the circumference, that area is called a segment. Okay. Now you can have it breaks the circle into two pieces. The smaller of the two pieces is called the minor segment, and the larger of the two pieces is called the major segment. Very clever mathematicians, very clever. Likewise, if you are looking at an arc, if we make this point and this point the bounds on an arc, we get a small arc here, right? It's called the minor arc from this point to this point. And if on the other side you get a major arc, it breaks it up into two pieces, right? There. Okay, so just some terminology before we go on. All right, so we want to be able to calculate these things. So in calculating arc length, the arc length is the amount of crust on the pizza that you get. There's some beautiful equations that you'll always have available to you that you can use to find these. I really hope that you don't memorize these. The idea makes sense, and I'll show you where it comes from. And it just comes from this idea that there should be an equal ratio between your angle and the total angle, and the amount of crust and the total crust, which is the circumference. So let me show you how where these equations come from, but I hope you never use them, you just use this idea. So think about this. Let me move him for a second. Let's make our own circle. There we go. And let's say theoretically they said this is a 90-degree angle, and our radius is, I don't know, 5, something like that. And they want to find this amount of crust that you get, right? The arc length. I know that the angle that we have is 90 out of the total angle, 360. That ratio, right? This is like we have a quarter of the total angle. We have 90 out of 360. So you should get a quarter of the crust, right? And so therefore you can calculate L out of the circumference is 2 pi r, and they told us r is 5, right? So you can set up this proportion and say, well, this is really 1/4. If you simplify this side, this is L over 10 pi. And therefore you have 4L equals 10 pi, and if you simplify that, it becomes what? 10 pi fourths, or 2 pi, or 5 pi halves, sorry, 5 pi halves, right? This will do the same thing for you, right? Let me show you where this comes from, just briefly. Let's do this in radians. If we have theta, right? This equation comes from the same thing. This says if we have angle theta over the total angle, which is 2 pi, I'm going to pretend it's in radians, so we derive this one and not this one. You get your arc length, which is L over the circumference, which is 2 pi r, right? And And if you cross multiply these, you get 2 pi r theta equals 2 pi rl. And your 2's and your pi's cancel out, and you get that, oh, and your, let's see, there's no r over here, sorry, there's no r over there. So you get L is equal to r theta, just like we'd expect. So if you like, use the equation, but you're going to have to look it up, right? You're going to be like, oh, which one was that? You never have to look up this idea, right? That the little angle divided by the whole angle all the way around is equal to this arc length divided by the whole way around. They're proportional. They're the same ratio, right? You'll never have to think about how to do that. You'll never have to look this up. Oh, grabbing my face. You'll never have to look this up. I think these are ridiculous. So let's try one in radians. Sorry, pause. Let's call this pi thirds just for fun. Call that pi thirds, and let's call this 2. I want to do it this way. I know it's longer, but in 3 months you're going to forget this stupid formula, but you won't forget this understanding that the ratios are the same. So I'm going to try it with this. So I know that pi thirds of the distance around divided by the total distance around, 2 pi, right? That's the distance, that's the angle subtended when you go all the way around the circle, should be the same ratio as this arc length L over all the arc length, which is called circumference, which is 2 pi r. And they gave us r, or I made up r. Fine. If you cross multiply, you get 2 pi L here, and on this side you get 4 pi times pi over 3. So times pi over 3. All right, and then you can start slicing and dicing. There's a 2 pi's there, so they cancel out, and then divide by 2. So r ends up being 4 pi. When you multiply by the denominator, 4 pi over 6. If you're not sure about the fractions, come see me. And that becomes 2 pi thirds. Cool? It's not that much long. I know it's a little bit longer, but it's not that much longer from doing this. Oh, I don't know how to do that. Find the booklet, right? Look up the equation, figure out if it's the right one, write it down, and then you say, oh, okay, so now I know that my equation is L equals pi times r, theta times r, and theta was pi over 3, and r was 2. I erased it, sorry about that. So this should be 2 pi thirds, right? Certainly longer, but by the time you regurgitate this stupid equation, it's not that much longer. I encourage you to use this understanding and not these ridiculous formulas. Sorry, is my personal bias coming out? All right, so sometimes we also need to calculate the area of the sector, which is like the area of the piece of pizza. So it's the same sort of idea. This area over the total area of the whole circle should be the same ratio as the angle you want over the total angle around. So let's try that. We were using pi thirds or something like that as an example, and r we were using as 2. So let's try that. The little angle here would be pi thirds. The ratio between that and the full angle, which is all the way around, that relationship should be the same relationship as the area that we're looking for over the total area, which is pi r squared. R here is 2, so pi times 2 squared. You can cross multiply, so 2 pi a should be pi times 4 pi, right? 4 pi and another pi all over 3. If you're not sure about fractions, come see me. And then what's nice about that is your pi's cancel out, and when you divide by 2, this 2 pops into the denominator and it cancels out with this, and so you're left with the area is 2 pi thirds. Cool. You can of course use their ridiculous formula that they have in the textbook, and I'll show you how that's derived in a second, but So it's not any uglier, and you'll never remember that. There's too much to do. So if you want to try to use it with that, it's half theta r squared, and half theta was pi thirds, so this is pi over 3, and r squared was 2, so r was 2, r squared is 4, so this becomes 4 pi over 6, which becomes 2 pi thirds, right there, right? And you'll never have to look this up, right? It's just like the area, the small area over the big area equals the small area over the big, small angle over the big angle. Great. If you're interested in the derivation, it's exactly the same thing, but it's just with variables. So if you're interested, check it out. If you're not, fast forward me, but here's the derivation. The angle we want is theta, the total angle is 2 pi, the sector area is A, and the total area is pi r squared. And so if we're trying to solve for A, we cross multiply, so 2 pi A equals theta times pi times r squared, and the pi cancels out with the pi, and so the area divided by 2, so you get area is 1 divided by 2 is like multiplying by a half, so half theta r squared. Sweet, there it is. You do the same thing with angle as 360 if you're trying to derive the other one. All right, so find the arc length and area if you got a radius of 12 and an angle of 3 radians. Just for example, 1 radian is around 60 degrees, so 3 radians might be around there, just for instance. So let's go for the arc length first. Here are the solutions, just if you'd like. You can use the ridiculous formula if you'd like. I'll make fun of you for it. But let's try the arc length. I know this, let's call it L. So the angle here, which is 3 radians, over the total, which is 2 pi, should be the same relationship as the amount of crust you get over the total amount of crust on the pizza, which we call the circumference. So that's 2 pi r. They gave us r, which was 12. Great. You can probably simplify right from here. Multiply both sides by 2 pi. Those cancel out. And then cross multiply. And so you get 1 times L equals 3 times 12, so 36. Great. Same thing with the area. We know that 3 over 2 pi, the angle over the total angle, should be the same thing as this area over the total area, which we can do, I'm doing purple, over the total area. Okay, kind of making a mess out of it, but that's okay. So it's little sector area over total area, which is pi times r squared, and we know r is 12, so 12 squared. Great. There's pi's in the denominators, so let's cancel those out, and so this ends up being 2a is 3 times 144, and so therefore you can divide by 2, and you get 3 times whatever 140, yeah, for 144, and then divide by 2, and I'm guessing it's 216. If it's not, let me know. Great, so that's all we want you to be able to do. Arc length and sector area. You use the understanding and not the area formulas because they're kind of ridiculous. Okay, bye.